Hello. So far we have been into the quantitative analysis where we are trying to understand the velocity analysis, and we have understood the velocity analysis, and in this session we'll try to understand the acceleration analysis through the graphical solution, that is velocity and acceleration polygons. Now, as in the first case or the first phase, we have understood the motion, which is, let us say, the displacement, and the rate of change of displacement as dx by dt, which we are calling this to be as velocity. Now this is linear motion and angular motion will be theta. So angular velocity is d theta by dt. Now we'll try to understand the acceleration part. So acceleration is rate of change of velocity. So here the angular acceleration will be this. So this is what we are trying to interpret in this session. Now, as we have seen, if we take the example of slider crank mechanism, now here we have seen that the crank will have a pure rotational motion. The slider is having pure linear motion, and the connecting rod is having a combination of motion. So what we are doing in velocity analysis is we are trying to determine velocities of all the joints, and then we can correlate. So this velocity here, which is angular, and here which is linear, so we are in a position in terms of the instantaneous velocities. So we are in velocity analysis, we are finding out the instantaneous velocities of all the joints, and we can then correlate. So, and as well in the velocity polygon, once the velocity polygon is complete, we can then determine the velocity of any point on that link, right? And this relation as well we have seen, where v is equal to r omega, where r is the radius of rotation of the point under consideration, and omega is the angular velocity of that particular link on which we have considered that particular point. So here now we'll try to understand. So acceleration of a particle along a circular path, right? So we are trying to understand. So as we know, these joints are having relative motion, so they are having into a kind of angular or combinations of motions, right? So now if we consider that there is a particle which is, say, following or which is moving along a circular path, and at one instant, let us say, the point is at location P, and it is moving with an angular velocity of omega. So after, let us say, an infinitesimally small time interval, so maybe it reaches to another location which is Q, and let us say at this infinitesimally small time interval, the displacement is infinitesimally small del theta. Now if we see the instantaneous velocity of this particle at the location P will be the tangential path, so perpendicular to the radius. So I can say this is the linear velocity or instantaneous velocity of P with respect to O, and at this instant the velocity is, let us say, instantaneous velocity will be perpendicular to this. Now if this velocity is v and we are saying that it is accelerating, then definitely, so maybe if it is accelerating, so here the velocity is changed velocity, some v plus del v. Now when we interpret this through the velocity polygon, now for this if I want to draw or get the velocity polygon, So according to scale and all, if I see, so it is say, let us say the particle is moving about O, then this is say O. So velocity vector of the particle at the location P will be tangential to the path. So let us say this is point P and this is velocity V at this instant, and after del t, so velocity vector of particle at the location Q will be this. So let us say this is Q and the magnitude of this velocity is V plus del V. Now what is acceleration? Acceleration is rate of change of velocity. So that means I need to first understand what will be the change in the velocity. So change in the velocity, if I want to see in the vector polygon, then this vector PQ will be the change in the velocity, right? So that means the acceleration. So now when you see this vector PQ, so this PQ is the absolute acceleration of that particle with respect to O, which is change in velocity. So maybe I can say it is PQ by del T. Fine. Now if I want to interpret or if I want to find out this particular vector, now in that case I'll have to resolve this into two components, right? So to reach Q with the help of two components, so one is, I can say this, so I have to move in this direction, and to reach Q, so the other component will be perpendicular to this one, so it will be this. So from here, so I move it this way, so let us say this point is R. So this will be the change in velocity components, this PR and PQ. So if you consider at the given instant, at this instant, so this is one component which is tangential to the path. So hence we are calling, or this PR is the tangential component of acceleration, and this RQ if you see at this given instant, it is towards O. So this is called as the centripetal component of acceleration. So now if I determine these two values or these two components, then I can find out the absolute acceleration. So absolute acceleration, I can say this absolute acceleration will be, the absolute acceleration will be the vector sum of tangential component and the centripetal component of that particular point. Fine. So first then I'll have to find out the tangential component of acceleration. So for this, if I say what is tangential, so tangential component of acceleration of this particle will be equal to this is the velocity, so this is PR by del T. Now what is PR? I can say it is OR minus OP. I can say that this PR is equal to OR minus OP by del T. Now what is OR? If you see, then the inclination between these two vectors will be del theta. Now what is OR? Now OR, if you see, it is the adjacent side of this right angled triangle. So I can say this OR will be OQ cos del theta. So it will be OQ cos del theta minus OP by del theta. Or I can say that what is OQ? OQ is V plus del V cos of del theta minus what is OP? OP is V by del T. Fine. Now when theta is very small, cos theta is 1, so I can say, so if I apply these conditions, it will be V plus del V minus V upon del T. So this gets cancelled, so I get this as del V by del T. So if I apply the limit conditions now, so I get the tangential component of acceleration to be equal to dV by dt. Fine. So we are getting tangential component of acceleration to be as dV by dt. And what is V? V is equal to r omega. So we can say it is d. So tangential component is equal to d of r omega by dt. So r is constant, so I can say tangential component, this is equal to r d omega by dt. Now what is omega? Omega is the angular velocity. So it is change in, so d omega by dt will be the angular acceleration. So it will be r alpha. So I can say here, so I can write here, the tangential component of acceleration is r or say dv by dt, or it is r alpha. Right? Now if you see, it is purely dv by dt. That means simply the change in the magnitude. The tangential component of acceleration will be simply the change in magnitude. So if omega changes the tangential component of, then only the particle will have the tangential component of acceleration. Fine. So now so this is one component which we have understood, and the second will be the centripetal or radial component, centripetal component of acceleration. Now what is centripetal component of acceleration? It is RQ. So centripetal component of acceleration will be RQ or QR by del T. Now what is RQ here? So it is opposite side, so it will be simply OQ sine del theta. So it will be OQ sine del theta. And what is OQ? OQ is V plus del V of sine del theta by del T. Now if for theta, if theta is very small, then sine theta is equal to theta, right? So I can say the centripetal component of acceleration is equal to V del theta, right? Because theta is very small, so it is del theta plus del V del theta by del T. Now if you see, product of two very small values will be again a smaller value. So I can very well neglect this part. So that means the centripetal component of acceleration is V del theta by del T. So when I apply the limiting conditions for del theta or del T, so I get the centripetal component of acceleration to be V d theta by dt. D theta by dt is angular velocity omega, right? And what is angular velocity? We have again the relation V is equal to R omega. So omega is equal to V by R, right? So by this we can say it will come out to be V square by R. So this is the centripetal component of acceleration. Fine. So the centripetal component of acceleration is V square R. So that means one thing is clear here then. If r is infinite, now if the radius of rotation is infinite, then the body is having only linear motion, so this value will be 0. Then in that case it will have only the tangential component, which is dv by dt, right? So simply the change in the magnitude of the velocity will be the component, right? So that is how. And if the velocity is uniform, if the velocity is in uniform, if it is not changing, if it is constant, then in that case, then dv by dt will be 0. So in that case, so if a particle is rotating with a constant velocity, so there is no change in v is equal to r omega. So if that omega is not changing, so alpha is not changing, so in that case it will not have any tangential component of acceleration, it will have only the centripetal component of acceleration. And one thing we have to understand here, the direction of this acceleration, these are all vector quantities, right? So the direction of this vector will be parallel to the tangential path of that given instant, and the direction of the centripetal component of the velocity vector will be always pointed towards the center of rotation. Again, I have told you, if you see this vector polygon, if you see this component, if I want to reach to Q, it has to move here and then come down. So if we are coming down, if you see this vector and put it at this instant, you will see that this vector is pointed towards the center of rotation. So the the acceleration vector directions of the tangential component will be parallel to the tangential path, and it will depend on the motion. So if it is accelerating, then the direction of this vector will be same as that of the motion. And if this body is retarding, then in that case we have considered here as v plus del v. So we are assuming the condition to be accelerating. Now if it is retarding, then in that case the acceleration will be in the negative direction. So the vector will be parallel to the tangential path, but it will be in the opposite direction. So that is how we can say now the absolute acceleration of that particle will be vector sum of these two components. Fine. So let us try to apply this. So it is now evident from this particular analysis, when we want to determine the accelerations in a given mechanism. So first we need to find out the tangential component. So tangential component and as well as the centripetal component. So as we have seen, the centripetal component of acceleration is v square by r, where v is the instantaneous velocity, and the tangential component we have seen it is r alpha, where alpha is the angular acceleration. Now let us try to interpret it with the help of, say, link. So this is link number 1, which we have taken as frame, and let us say this is link number 2, and there is some point A, and this is turning with an angular velocity of omega, right? And to understand, let us not consider this to be uniform. It is having as well an angular acceleration, let us say alpha. So this is omega of OA link, and this is alpha of OA link. So now when I want to find out the acceleration of point A, so we'll have to first find out the instantaneous velocity of this point, right? So this will be the radius of rotation for A. So when this is turning in this direction, the instantaneous velocity vector, so as it is turning in this direction, so this velocity vector will be in this direction. So this is velocity of A with respect to O, and it will be perpendicular to OA, right? So now if I want to draw the velocity vector, so if you want to draw the velocity vector polygon or velocity polygon, so taking appropriate scale, so I can mark this as the pole. So velocity vector is pointed in this direction, so it is moving in this direction. So this is A, and this is velocity of A with respect to O. So as if now if we see the velocity polygon is done here. Now I have to go for so I want to determine now the acceleration. So we'll go for the acceleration polygon. Again I'll have to take an appropriate scale and accordingly. So first we need to find out the magnitude. Direction we can understand. So now acceleration of A. So absolute acceleration of A with respect to O will have two components. Fine. So one component will be the centripetal component of A with respect to O, which is equal to velocity of A with respect to O square by R. R for this is OA. And the tangential component of A with respect to O will be R alpha. So OA into alpha of or angular acceleration of A. Fine. So we know this value from the vector polygon. So we can find out now if this is given to me. Fine. So right now if I consider this to be as the input link. So now I'll first locate the vector polygon. For vector polygon I'll locate the pole. So pole is, let us say this point is O. So now it will have two components. Which are the two components? The centripetal component of acceleration. Centripetal component is acted, the vector is towards the center of rotation. So A is rotating about O. So this vector, this is the centripetal component, and perpendicular alpha we have shown turning clockwise. So this will be tangential component. So now when I want to determine, so first I will draw the centripetal component of acceleration, which is this. So parallel to this I can draw. So this is O. So this will be parallel to this. So this I get as the centripetal component of A with respect to O. But this is not the absolute location of A. So I name this as A dash. And the tangential component, now as alpha is in this direction, so tangential component. So magnitude, if I know A, I can find out this value. So maybe I can draw this vector, the tangential component perpendicular to this. So it will be in this direction. So let us say this is the tangential component of A with respect to O. Then now we can say when we join, so this point will come out to be as the final point as A or absolute location of A. So this vector will be the absolute acceleration of A with respect to O. So that is how when we apply these conditions in a given mechanism, so we can determine again the accelerations of each and every joint in that mechanism, and once the polygon is done we can find out then the acceleration of any point on that mechanism. So that is how we can do the acceleration analysis. So that's all in this session.